A very good morning to all of you. This is the second lecture of module number 5. That's last module. In today's lecture, we are first of all going to discuss the design aspects of filters. Right here, design of harmonic filters. Harmonic filters. I will try to give the design aspects of two types of harmonic filters. One is single tune filter and another is double tune filter. Let me first of all take single tune filter. Okay, this is our single tune filter. C, L and R. C, L, R. This is the harmonic current flowing through it is IH. Okay, now I can write that filter impedance is given by, so let me write filter impedance is ZF. ZF means filter impedance. It is R plus J times XL minus XC. J times XL is omega L minus XC is 1 by omega C, right? Now omega n, that is the resonant frequencies, we know that is 1 by under root LC. We know it from basic theory of this basic circuit theory. The resonant frequency is given by this equation. Now if there is a deviation of frequency, for example, if you design this harmonic filter for fifth harmonic frequency, so it will suppress the fifth harmonic frequency component of the current. It will act as a sink for the fifth harmonic component of current, and it will not allow that fifth harmonic component of current to flow in the line. It will arrest that fifth harmonic component. But there may be frequency deviation, so that frequency, a small frequency deviation may be there. I can write frequency deviation. It is given by, let us assume frequency deviation is delta. So delta is equal to omega minus omega n by omega n. This is the equation for frequency deviation. So from this delta omega n is equal to omega minus omega n. So from this omega will be equal to omega n times 1 plus delta. Okay, this is the frequency. Omega is omega n times 1 plus delta, where delta is the slight or small frequency deviation. Now I can write here that reactance of the filter at resonant frequency. Resonant frequency is the frequency at which this filter is tuned. So at that time the reactance will be given by, so I will write reactance at resonant frequency. It is given by X is equal to omega L. Omega n into L, or that is given by under root of L by C. Why? Because omega n is, as you know, omega n is 1 by under root LC. If you substitute that here and you solve it, it will be under root of L by C. So therefore, filter impedance will be given by ZF is equal to R plus J times, if you substitute there and solve it, it will be omega into L by omega n minus 1 by omega n omega into C. If you multiply it by omega n, actually in actual figure, in actual equation, there is no omega n. So if you divide this by omega n, this also by omega n, you have to multiply it also by omega n. So I can also write filter impedance equal to R times, if I take R out, I mean in this equation, if I take R out, it will be 1 plus J times omega L by R minus 1 by omega C by R. R times 1 plus J into omega L by R minus 1 by omega C R. This is another way of writing it. Now reactive power generated will be given by Q is equal to, quality factor, not reactive power. Reactive power we'll consider later on. First of all, let us write the expression for quality factor of the filter. So quality factor of the filter. So quality factor is given by omega n L by R. I hope you remember it from your basic circuit theory. So that is also given by 1 by omega n C into R. This is the quality factor of the coil. Now, therefore, in terms of quality factor, I will write here in terms of quality factor of the coil, or in terms of quality factor, the expression for filter impedance is given by this. ZF is equal to R times 1 plus JQ omega by omega n minus omega n by omega. I mean, this is your actual equation. This is the equation. Here we know omega Q is omega n L by R. Similarly here, this is ZF is equal to R times 1 plus J omega L by R minus 1 by omega CR. So if you substitute Q equal to omega n L by R and simplify this equation, it comes out to be this. Filter impedance in terms of quality factor is ZF equal to R times 1 plus JQ into omega by omega n minus omega n by omega after manipulation, after simplification. I am skipping some steps. You can do those steps yourself. As omega is equal to omega n times 1 plus delta, we have already written it earlier. Here you already know we have written omega is equal to omega n into 1 plus delta. So we can substitute it here. So therefore, ZF filter impedance is equal to R times 1 plus JQ. Now omega is omega n times 1 plus delta. So you can, in this equation, you can substitute omega equal to omega n into 1 plus delta, and you can solve the equation, simplify it. After substitution and simplification, you will finally get this equation, Q times 1 plus delta minus 1 by 1 plus delta. Okay, after simplification. Or I can also write ZF equal to R times 1 plus JQ. If I take delta out, what I get inside is 2 plus delta divided by 1 plus delta. I mean, if I take delta, I mean, if I solve this equation and I take delta also outside, then this will be 1 plus JQ, delta also outside, and inside it will be 2 plus delta by 1 plus delta. So this is the final expression for filter impedance corresponding to a particular harmonic frequency, when it is tuned to a particular harmonic frequency, right? I can also write as delta is very small. Delta is the frequency deviation. It is very, very small. So therefore, this equation will get modified to ZF equal to R times 1 plus J 2Q delta. I mean, delta is very, very small. You can assume delta is very, very small and then simplify this equation. This equation will become ZF equal to R times 1 plus JQ delta. Okay, so this is the expression for filter impedance. I can also write filter impedance. So let me highlight it. Also, filter impedance can also be written as ZF equal to X naught K. This is another way of writing filter impedance, where X naught is equal to under root of L by C. And what is K? K is equal to 1 by Q plus J delta times 2 plus delta divided by 1 plus delta. Okay, this is 1 plus JQ delta, 2 plus delta by 1 plus delta. Here also, I mean, if you substitute, make it equal to 1 by equal to Q. So K is equal to 1 by Q plus J delta times 2 plus delta by 1 plus delta. I mean, if you manipulate it, you solve it, I mean, simplify it, you can write it in this form, ZF equal to X naught K, where X naught is under root of L by C and K is 1 by Q plus J delta times 2 plus delta by 1 plus delta. So for delta, for quality factor to be infinite, I mean, if you have an ideal inductor coil, see, inductor is a part of your filter. This is your inductor. If this inductor coil has very high, I mean, infinite quality factor, that means if it is ideal, this filter coil, then in that case you can write K equal to J delta, because 1 by infinity is, so this is 1 by infinity, so you can neglect it. So 1 by infinity is 0, so it will be J delta times 2 plus delta divided by 1 plus delta. So this is the final expression for K. Well, let me try to plot K with respect to delta. Let us see how K varies with delta. Now, variation of K with delta, I will again write filter impedance ZF is equal to K X naught, and X naught is equal to under root of L by C, and K for infinite delta is J delta, for infinite Q is J delta times 2 plus delta by 1 plus delta. So it's an imaginary component. So its variation of K with delta is like this. Delta is the frequency deviation. This is delta axis. This is 0, 0.001, because frequency deviation is very small, so that's what I am writing, 0.015, 0.02. Similarly on this side, minus 0.001, minus 0.015, and minus 0.02, and this is K. The K will vary like this. Let me show you variation of K. This is the first curve that you will get. This is for Q tending to infinity. I mean, if Q is infinite, then you will get this type of variation of K with delta. K will vary with delta for infinite Q like this. Okay, and I mean, what is your K actually? K here is plus 1 by Q. I mean, see, your K is J delta times 2 plus delta by 1 plus delta plus 1 by Q. For Q tending to infinite, this 1 by Q will be 0, then your K will be this. And if you plot this K, it will be like this. Now let us assume Q is not infinite. Q has some finite value. And for different values, we will plot variation of K with delta like this. This is 0.01. This is for Q equal to 125. This next curve is for Q equal to 100. And this curve is for Q equal to 75. See, Q is infinite, then this is variation of K with delta. For Q equal to 125, this is the variation of K with delta. For Q equal to 100, this is the variation of K with delta. And for Q equal to 75, which is a finite positive value, this is the variation of K with delta. Okay, so this may be your 0.02, then this may be 0.03, and so on. So this equation shows variation, or this graph shows variation of K with delta for different values of Q. For Q equal to infinity, Q equal to 125, Q equal to 100, Q equal to 75. So once you know quality factor of the filter inductance, okay, and you know how K varies with delta, then you have this equation with you. Filter impedance is K times X naught. K you can find from this graph, okay, for a given value of Q. So you can substitute it here, and X naught is under root of L by C. You can find filter impedance. Once you know filter impedance for a particular harmonic frequency, what will your filter do? It will exactly arrest that harmonic of that particular frequency within small frequency deviations, delta. Delta is the frequency deviation. Okay, so it will prove very effective. Then once you substitute this ZF equal to K X naught, you will get the filter impedance. Once you know the filter impedance, you can find L and you can find C. Okay, and you can also find R. Okay, and in this way you can design this single tuned filter. In single tuned filter, the main thing is that you must know L, you must know C, you must know R. Okay, L and R, once you plot, once you know you choose a filter inductance of a particular quality factor. Then once you know the quality factor, say quality factor is 100, then this is the variation of K with with delta for 100. You know that. So from that, you can substitute it in this equation. You can find filter impedance, K into X naught. And once you know filter impedance, you can know L and you can know R. How do you know L and R? Because you know your quality factor is omega n L by R. Omega n is the harmonic frequency at which you are resonating your filter. L you know and R you can find. Once you know L, you know omega n, you know quality factor, you can find R. Once you know R, then from this equation you can find C. This is how you design the filter. Okay, so this is design of single tuned filter. Let us quickly go for design of double tuned filter. So I will now write double tuned filter. Double tuned filter. Double tuned filter is tuned to two different harmonic frequencies. That means it is a single filter, but it arrests two harmonics in the current. Say for example, you may tune it for 5th harmonic and 7th harmonic. So it will arrest both the currents effectively, 5th harmonic component of current as well as 7th harmonic component of current. So it looks like this. This is R, L, C. This is another R, L, C. So this is your double tune filter. The R1, L1, C1, R1, R2, L2, C2. Okay, so this is tuned to one frequency, one harmonic frequency. Let us suppose for 6 pulse converter, it is tuned to 5th harmonic frequency, and this single tune, see, your double tune filter comprises of 2 single tune filters. This is tuned to one harmonic frequency, and this is tuned to another harmonic frequency, tuned to second or other harmonic frequency. If you are using this double tune filter for a 6 pulse converter, then this filter you will tune to 5th harmonic, you will tune this filter for 7th harmonic. So it will simultaneously suppress both 5th as well as 7th harmonic component of the frequency. And if you are using it for a 12 pulse converter, in a 12 pulse converter, the most predominant harmonic is 11th followed by 13th. Then this part of the filter will be tuned to 11th harmonic frequency, and this part of the filter will be tuned to 13th harmonic frequency, and it will arrest 11th as well as 13th harmonic components of frequency. This is if your double tune filter comprises of 2 single tune filters. So first is comprising of or composed of 2 single tune filters. Single tuned filters. In that case, your double tune filter will look like this. But you may have a double tune filter which is also called single double tune filter. I mean, it will not comprise of 2 single tune filters. It will be a single double tune filter, and it will look like this. It will look like this: R, L, R, C, and L, C. So this is double tuned filter. So what I mean to say, there are 2 ways of designing or constructing your double tune filter. One way is that you make your single double tune filter by 2 single tune filters. In that case, it will comprise of 2 single tune filters, composed of 2 single tune filter. One single tune filter is tuned to one harmonic frequency, and another single tune filter is tuned to other harmonic frequency. But the best way is that you have a single double tune filter. In that case, it comprises of these components: R, you can say R1, L1, R2, C1, L2, C2. Okay, in that case, it comprises of, this is the structure of a single double tune filter. Now, I can write again, frequency deviation is given by omega minus omega n by omega n. So delta is equal to omega by omega n minus 1. So delta is equal to, I can write omega under root of 1. Omega n is 1 by, omega n is, you already know, is under root of L by C. Omega n is equal to under root of L by C. So what is 1 by omega n? That is under root of C by L minus 1. Okay, because omega n is under root of L by C. So what is 1 by omega n? That is under root of C by L. So it is, delta is equal to omega times under root of C by L minus 1. So what is change in the frequency? Del delta. Del delta is del omega by omega plus 1 by 2, which is given by this equation. Del C by C plus del L by L. This is if there is a deviation in the frequency, it is represented like this. Now, once you design the double tune filter, Now the question is, I have already told you that there are two purposes of a filter. Number one, to suppress the harmonics of a particular harmonic frequency, and number two, to provide some reactive power compensation. Let us see how it provides the reactive power compensation. So after this double tune filter, if I take again single tune filter, R, L and C, this is my single tune filter, R, L, C. Let us see how it provides reactive power compensation. Reactive power compensation. It is not designed for providing 100% reactive power compensation. Its main primary job is to suppress the harmonics, but simultaneously some sort of reactive power compensation can also be provided to it. So in that case, reactive power, I will write here, reactive power generated by the filter is given by Q is equal to, see, Q is reactive power. When you find the reactive power, you have to multiply it by fundamental component of current, because harmonic component of current do not contribute to reactive power. It is the fundamental component of current which contributes to reactive power. So it is I1 square times XL minus XC, because you have here L as well as C. XL is the inductance, reactive inductance, okay, and C is the XL is the inductive reactance, and XC is the capacitive reactance. Okay, so reactive power then generates, C will generate the reactive power and L will consume the reactive power. So therefore Q will be given by I1 square times what is XL? XL is omega 1L minus what is XC? It is 1 by omega 1C. Okay, and we so Q is equal to, if I take I write I1 square omega 1L, I take out. What I get inside, omega 1L I have taken out, so I will get 1 minus 1 by, so when I take omega 1L out, it will divide this denominator. So omega 1 into omega 1 will be omega 1 square, then L will be there and C will also be there. Okay, now let us call this equation as equation 1. As we know, omega n, that is the resonant frequency, the frequency at which your filter is tuned, is given by 1 by under root LC. So therefore omega n square is given by 1 by LC. So therefore, what is reactive power generated? Reactive power generated is equal to I1 square omega 1L from this equation times 1 minus, I can write omega n square by omega 1 square. Okay, because what is your omega n? Omega n square is 1 by LC. And if you write here 1 by, see, it is here 1 by LC. What is 1 by LC? 1 by LC is omega n square. So I am substituting 1 by LC, I am replacing it by omega n square. And then denominator may already there is omega 1 square. So therefore what I am doing, 1 by LC is omega n square, I already know. So I am replacing this 1 by NC by omega n square divided by omega 1 square. So I will again write Q is equal to I1 square omega 1 L times 1 minus omega n square by omega 1 square. This is, say, equation 2. Now we know that omega n is equal to H times omega 1. Omega n is the harmonic frequency, and it is harmonic order times fundamental frequency. For example, what is omega 5? That is 5 omega 1. Omega 7 is 7 omega 1. Omega 11 is 11 omega 1. Omega 13 is 13 omega 1, omega 17 is 17 omega 1, and so on. So in general, omega n, harmonic frequency, is given by harmonic order times fundamental component of frequency. That is, omega n is H times omega 1. So you can substitute in this equation. So therefore, from equation 2, I will get Q is equal to I1 square omega 1 L times 1 minus, it is omega n square. What is omega n? Omega n is H omega 1. So it is H square omega 1 square divided by omega 1 square. Now omega 1 square and omega 1 square cancel. So this will give me reactive power equal to I1 square omega 1 L times 1 minus H square. So it is 1 minus H square. Now H is the harmonic order. So for a 6 pulse converter, what type of harmonics are there in the current? H, 5th harmonic is there, 7th harmonic is there, 11th harmonic is there, 13th, 17th, 19th, 23rd, 25th, and so on. And for a 12 pulse converter, what type of harmonics are there? Let me write. For a 12 pulse converter, H is equal to most predominant harmonic is 11th, because 5th and 7th harmonics are not there. 11th, 13th, then 23rd, 25th, and so on. So if you substitute H for 6 pulse converter, 5, so it will be 1 minus 5 square, 1 minus 25. Then this is, if you substitute, if you have tuned your filter to 5th harmonic frequency. So what is the reactive power generated or consumed by your filter? That's I1 square omega 1 L times 1 minus 5 square. 1 minus 5 square means 1 minus 25. So it will come out to be negative. Similarly, if your filter is designed or it is tuned to 7th harmonic, so it will be 1 minus 7 square, 1 minus 49. That will again be negative. For a 12 pulse converter, if the filter is tuned to suppress 11th harmonic, so 1 minus 11 square, 1 minus 121, or 13th harmonic, 1 minus 13 square. So for any value of H, whether it is 5, 7, 11, 13, or any, so 1 minus H square will be always negative. So which means Q will always be negative. And what does negative reactive power mean? Negative reactive power means that your filter, single tuned filter, it generates reactive power. So if reactive power would have been positive, that means it is consuming reactive power. But negative reactive power means it is generating reactive power. It is injecting reactive power into bus Q1. So therefore, negative reactive power means reactive power is generated by harmonic filter, whether it is single tuned harmonic filter or double tuned harmonic filter. Here I have shown for single tuned harmonic filter, and injected into the system, AC system, for some reactive power compensation. So it provides some reactive power compensation. Therefore, it is clear that your filters, whether it is single tuned filter or double tuned filter, they do not suppress the harmonics only, harmonics of a particular frequency, but they provide some reactive power compensation also. For example, if this single tuned filter is tuned to 5th harmonic frequency, I mean, we are designing it for suppressing 5th harmonic component of current. So no doubt, we from the previous, just few moments back, we have seen how to design a single tuned filter. From those equations, we can find the value of R, L, and C. And it will suppress that it will eliminate the 5th harmonic component of current. Okay, but simultaneously it will provide reactive power compensation. And how much reactive power compensation it will provide? I1 square omega 1 L times 1 minus 5 square, because H is equal to 5. Okay, so 1 minus 5 square means 1 minus 25. 1 minus 25 means minus 24. Minus 24 multiplied by fundamental component of current. You already know what is the fundamental component of current. You know what is the fundamental frequency, that is 50 Hertz. And you already know what is the value of this L. Okay, L, you know what is this L. If you substitute here, you can exactly find that how much reactive power compensation it provides. And this reactive power always comes out to be negative. That means your filter is not absorbing reactive power. It is generating reactive power, injecting that into the AC system for some reactive power compensation. And finally, you should write that cost of this harmonic filter. What is the cost of harmonic filter? Generally, the thumb rule is that cost of harmonic filter is 5 to 10%. 5% to 10% of cost of terminal equipment. Your terminal equipment comprises of converters, converter transformer, etc. If the cost of terminal equipment is say $1,000, then the cost of harmonic filter that you are putting there for suppressing a particular harmonic and providing some reactive power compensation is 5 to 10% of cost of terminal equipment. So that is about how reactive power compensation and how much reactive power compensation is provided by a single tuned filter. Similarly, we can find the reactive power compensation by double tuned filter. So this completes our discussions on design and reactive power compensation of single tuned and double tuned harmonic filters. Let us go ahead. Now, We already know that our harmonic filter suppresses harmonics and it provides some reactive power compensation. But the problem with these harmonic filters is that they are very costly. Okay, because you have seen cost of one filter is 5, or cost of harmonic filter is 5 to 10% of cost of terminal equipment. I've already given you an example. Is, for example, if your terminal equipment costs say $100,000, your filters will cost 10 to 15% of that. It is a huge amount. Okay, so but there is a way of designing a filter for minimum cost. Let us see how we can design a filter for minimum cost. I will write here minimum cost tuned filter design. Minimum cost tuned filter design. Let us see what are the criteria of designing a filter for minimum cost. See, your filter has a capacitor and it has an inductor also. So I will write here rating of tuned capacitor is given by reactive power generated by it. Reactive power, and the reactive power is in megawatts. Megawatts supplied by it, injected by it, or generated by it. Okay, so that is given by, I mean, if I know how much reactive power, see, you already have reactive power compensation equipment in your HVDC system. That reactive power compensation provides the maximum reactive power compensation, and then your harmonic filter also provides some reactive power compensation. If you want to design your filter for minimum cost, then you have to fix how much reactive power it has to compensate, or how much reactive power the filter has to generate or supply. Which part of the filter supplies the reactive power? See, if this is your filter, it comprises of R, L and C. It is the capacitor which generates the reactive power, which supplies the reactive power. Okay, inductor absorbs the reactive power. Out of this generated reactive power, some reactive power will be absorbed by inductor, and then rest will be supplied into the AC system. So it is the capacitor which decides how much reactive power has to be supplied. So therefore, reactive power, I will write here, reactive power supplied or generated by capacitor of the filter, because capacitor supplies or generates the reactive power, that is given by QCR is equal to, it is V1 square omega C plus IH square XCH. See, now problem is that your filter handles reactive power, this fundamental component of current as well as harmonic component of current also. Now your filter should supply the reactive power. So reactive power, it should supply corresponding to fundamental component of frequency. But simultaneously, see, your filter is designed to suppress some harmonic current, say IH. So corresponding to that harmonic current also, it generates some reactive power, which is called harmonic reactive power. Okay, so total reactive power supplied by or generated by this capacitor is fundamental reactive power plus harmonic reactive power. The expression for fundamental reactive power is V1 square V1 square by, see, reactive power by a capacitor is given by V square by XC. XC is 1 by LC, okay, 1 by omega C. So that will be equal to V square by 1 by omega C. That will be V square omega C. That's what I am writing here. V1 square omega C. Why 1? Because fundamental component of voltage. And in addition to this reactive power, fundamental reactive power, it generates reactive power corresponding to harmonic component of current also, because it arrests, it passes the harmonic component of current. Corresponding to that harmonic component of current, how much reactive power it is generating? I square into XCH, IH square into XCH. Okay, so that is given by QCR is equal to V1 square omega 1C plus IH square. What is XCH? You already know that XC is 1 by omega C. Okay, so what is XCH? That is equal to 1 by H omega 1C. Okay, because H means harmonic component. So you have to divide by H, you have to multiply it by H. So it is IH square. It is not IH square by omega 1C. It is IH square by H omega 1C, because which component of current it is handling? H harmonic component of current. So you have to multiply it by harmonic order. If it was handling only fundamental component of frequency, then it would have been I1 square by omega 1 C. But since it is handling harmonic component of current, say 5th, 7th, 11th or 30th, so it is IH square by H omega 1 C. Fine. Now let S, that is this rating of the capacitor. Rating of the capacitor is given by omega V1 square omega 1 C. Okay. So the fundamental reactive power decides its rating. So therefore QCR is equal to, it is V1 square omega 1 C. We have represented that by S. So it is S plus V1 square IH square by V1 square omega 1 CH. See what I have done here. What is here? It is V1 square omega 1 C plus IH square by H omega 1 C. Now omega 1 V1 square omega 1 C we have denoted by S, so I have replaced this first term by S. Second term was IH square by H omega 1 C, so it is IH square by H omega 1 C. But I have multiplied and divided it by V1 square. So therefore QCR will be equal to S plus V1 square IH square by SH. It's interesting to see. See, if your S is V1 square omega 1 C, what is V1 square omega 1 CH? It is SH. See, if I remove this H, I get V1 square omega 1 C, and we already know V1 square omega 1 C is S. That is this. What is V1 square omega 1 C multiplied by H? That is SH. So that means your filter is handling fundamental component of reactive power plus harmonic component of reactive power. So therefore QCR, the total reactive power generated by your capacitor, is S, that is fundamental reactive power, plus V1 square IH square by SH. Okay, just note it down, remember it, and call this equation as equation 1. So this gives your rating of capacitor. So this determines the megavar MVAR rating of filter capacitor. Capacitor is the part of your filter. So its rating is determined by how much reactive power it is generating. So how much reactive power it is generating? S plus V1 square IH square by SH. So this gives the rating of your capacitor. So similarly, you can find the rating of your inductor. Let us see how we find rating of the inductor. Now I will write here a rating of tuned inductor. We have found just now rating of tuned capacitor. Now let us find rating of tuned inductor. Rating of tuned inductor you can find if you know how much reactive power it is absorbing, because the inductor absorbs the reactive power. So how much reactive power it is absorbing? Reactive power absorbed by your inductor, that is given by QLR, is equal to, it is I square XL, that is I1 square omega 1 L, fundamental reactive power, it absorbs this much of fundamental reactive power, plus IH square XLH. Okay, this is the fundamental reactive power absorbed by it, and this is the reactive power at harmonic for harmonic component of current. IH square XL into H. Sorry, it is XLH subscript. This is IH square XLH. Okay, make a correction. So I can write QLR is equal to I1 square omega 1 L plus IH square H omega 1 L. So this is XLH, because XLH is equal to H times omega 1 L. Okay, XL is omega 1 L multiplied by H, so it is H times omega 1 L, harmonic order times the reactance, fundamental reactance. Fine, it's okay. So now we already know omega n, that is the frequency at which your filter is tuned. Tuned frequency is 1 by under root LC. So omega n square is 1 by LC. तो यहाँ से आप L निकाल सकते हैं. L is 1 by omega n square C, that is 1 by H square omega 1 square C. It is omega n square C. N is the harmonic order. So what is n? Omega n. Omega n is h omega 1. So it is h square omega 1 square c. So therefore, if I call this equation 2, so therefore from equation 2, you can substitute it in equation 2. We have, what do we have? The reactive power absorbed by inductor, tuned inductor, is equal to, it is given by, first term is I1 square omega 1 L. I will write it as it is, I1 square into omega 1 L. Omega 1 into, okay, fine, I1 square omega 1 into L. So I1 square omega 1 into, what is my L? Just now I have found L is equal to 1 by h square by omega 1 square. So I will substitute L by 1 by h square omega 1 square c. So what I have done, यहाँ पे L I have replaced by 1 by h square omega 1 square c, जो मैंने अभी निकाला. Plus second term is, what is my second term? IH square h omega 1 L. So it is IH square h omega 1 into L. L is again there, and you know L is 1 by h square omega 1 c, omega 1 square c, 1 by h square omega 1 square c. Fine. Now, if you further simplify it, QLR, you will find it comes out to be, see, omega 1 square goes, so I will get I1 square by h square omega 1 c plus यहाँ पे मेरा h और h square गया, so it is IH square by h omega 1 c. Omega 1 also goes with omega 1, this square, so it is IH square by h omega 1 c. Okay, so QLR is equal to, what is my h square omega 1, what is my, so I can write it as, what is my I1 square by omega 1 c? Just few moments back, this was S. S was V1 square omega 1 c, right? And this is also equal to, it is also equal to I1 square by omega 1 c. I1 square by omega 1 c. In terms of voltage, it is V1 square omega 1 c. In terms of current, it is I1 square by omega 1 c. So I1 square by omega 1 c is H. So in this equation, I1 square by omega 1 c is, S. So it is S by H square, because H square is already there. It's already there. Plus, I will write here V1 square IH square by HS. See, plus, V1 square H1 square H V1 square omega 1 c. So what I have done, I have multiplied by V1 square, multiplied and divided by V1 square. It was IH square by H omega 1 c. So I am multiplying by V1 square, ऊपर numerator और divide भी कर रहा हूँ V1 square से. So this will give me QLR equal to S by H square plus V1 square IH square, ये मैं ऐसे ही लिखूंगा, V1 square IH square by H times, what is V1 square omega 1 c? Okay, you can see from here, V1 square omega, this is V1 square omega 1 c, it is QCR. Here, V1 square omega 1 c, it is S. So I will replace it by S. So this is the reactive power absorbed by your inductor when it is tuned to a particular harmonic frequency. So if you know harmonic current, you know harmonic order. So it is S by H square plus V1 square IH square by HS. Okay. So this is the rating of your inductor, tuned inductor. What is the rating of your tuned capacitor? QCR in megawars. I will write here, its unit megawars hai, because reactive power is always in megawars. It is S plus V1 square IH square by SH. And what is the rating of your tuned inductor? It is S by H square plus V1 square IH square by HS. It is also in megawatts. Let us call this equation 3. So therefore, what is the total cost of filter? Total cost of filter is cost of inductor, tuned inductor plus cost of tuned capacitor. Let us find it out. So therefore, I should write total cost of tuned filter. Total cost of tuned filter is rating multiplied by cost per unit megavar. So that is given by K. Let us denote cost by K. K is equal to QRC into UC plus QRL into UL, where UC and UL are per unit cost in dollars per megavar of filter, capacitor and inductor respectively. So what is the total rating? Total rating is QRC plus QRL. So therefore, what is the cost? If cost of capacitor is UC dollars per megavar and cost of inductor is UL dollars per megavar. So UC is the cost of filter per megavar multiplied by rating of the capacitor, which is in megavars. So this will give total cost of capacitor. Plus, what is the total rating of inductor? That is QRL in megavars multiplied by cost per unit megavar. That is given UL. So multiply it by this. So this will give total cost of capacitor, tuned filter capacitor, and this will give total cost of tuned filter inductor. And this cost plus this cost will give you the total cost of the filter. या आपके फिल्टर का टोटल कॉस्ट मिलेगा. Okay, so now substitute K equal to, we already know what is QR. What is QR? QRC. This is your QRC. QRC is, or QCR is S plus V1 square IH square by SH. So I will substitute it here. In place of QRC, I will substitute S plus V1 square IH square by SH into UC, because UC is there, into plus QRL into UL. What is QRL? QRL we already know. अभी थोड़ी देर पहले हमने निकाला. It is S by H square plus V1 square IH square by HS. So it is S by H square plus V1 square IH square by SH into UL multiplied by UL. So this is the total cost of the filter. So let me expand it. K is equal to S into UC plus UC into this V1 square IH square by SH into UC plus S by H square into UL plus V1 square IH square by SH into UL. Fine. So this will give me K equal to, okay, so this is so if I take S out, okay, S इसमें है और S इसमें है. So if I take S out from these two terms, so I will get UC plus, यहाँ से भी मैं S out लेता हूँ, so it will be UL minus H square, UL by H square plus. Now if I take V1 square IH square by SH out, okay, so I will get V1 square IH square by SHS. What I get here? UC. और यहाँ क्या मिलेगा मुझे? Plus UL. Okay, so this is the final equation for cost of filter. So this means total cost of filter is AS plus B by S. Where what is A and what is B? Where A is UC plus UL by H square, and B is V1 square IH square into UC plus UL by H. This is A and this is B. Now for minimum cost, I have to design the filter for minimum cost. For minimum cost, this equation dk with respect to rating of the filter ds, I should substitute it equal to 0. So dk by ds should be equal to 0. So that means d by ds of as plus b by s is equal to 0. So this will give me a minus b by s square equal to 0. So this will give me S equal to under root of B by A. This is the condition for minimum cost of filter. The rating or the total megavars or total reactive power for which the filter should be designed, it is given by under root of B by A. I know what is B, I know what is A. I can find what is the total reactive power for which my filter should compensate, and corresponding to that reactive power, my filter will be designed for minimum cost. Okay, condition for minimum cost is S is equal to under root of B by A. So therefore, what is the minimum cost of the filter corresponding to this condition? So here I will write this is the condition for minimum cost of filter. Minimum cost of filter. And what is the minimum cost? I will write minimum cost, let me call that K min, is equal to, what is my filter cost? It is AS plus B by S. I already know. So K min, condition is A into S. Condition for minimum cost of filter is under root of B by A. So S is under root of B by A. So I will substitute it under root B by under root A plus B by S. B by S. So S is again under root B by under root A. So it will be under root of A by under root of B. And I substitute it in place of S here. Now that means K min, minimum cost of filter, will be equal to A under root B by under root A, rationalize it, multiplied by under root A, divided by under root A. Similarly, second term I will rationalize B into under root A by under root B, multiplied by under root B by under root B. So minimum cost of filter will be equal to, so under root A into under root A is A and A goes, so this is under root of AB plus, here under root B into under root B is B and B goes, so it is again under root of AB. So therefore minimum cost of filter K min is equal to 2 under root AB. I know what is A, I know what is B. Okay, if I substitute A and B here and multiply, take square root of that, multiply that by 2, that will give me the minimum cost of filter. So therefore I can plot the variation of cost of filter with a rating like this. So this is 0, 5, 10, 15, 20. S is megawatts per phase. This is x-axis, and y-axis is cost K. Okay, say $20, $40, or per unit 60, 80, and 100. This is the variation. This is AS. This curve is AS, and this curve is B by S. Because what is total cost of filter? Total cost of filter is AS plus B by S. So therefore total cost is sum of this curve plus this curve. If you add it, so this is the total cost of filter. This is total cost, which is equal to AS plus B by S. और इसका minimum cost ये, this is the minimum cost, K min. The minima of this, minimum peak, this is the minimum cost. And what is that minimum cost equal to? That is 2 under root of A into B. Okay, so this is how we find the minimum cost of filter. Once you know the condition for minimum cost, and we have already found what is the condition for minimum cost. Condition is that the total reactive power compensation by your tuned harmonic filter should be under root of B by A. And then if your filter generates only this much of reactive power, then the cost of filter will be minimum, and the cost will be given by 2 under root of A into B. And that is also confirmed by this curve. In this curve, this is first component of cost, AS. This is the second component of cost, B by S. This is the variation of cost with total reactive power generation, megawatts per phase. Okay, the total cost will be given by this curve. I should give it more slope. It is more slopey. Okay, like this. So total cost is AS plus B by S, and this minima of the curve is the minimum cost of the filter. Now let us try to design the filter for minimum cost. We will take an example. This is our say HVDC system. Let us suppose we have 4 bridges in series for high voltage operation. This is your bipolar HVDC link. This is YY connected transformer, and this is Y delta connected transformer. Similarly here, this is YY connected transformer, and this is Y delta connected transformer. So you have total 4 bridges per pole, okay? And then you have DC reactor, and this is ID, and this is plus minus VDR, rectifier side voltage. Let VD, that is DC voltage, is plus minus 300 kV. So we have a bipolar HVDC link plus minus 300 kV. It is a bipolar link, and it has 4 bridges per pole. It's a 12 pulse converter operation. 12 pulse operation. Okay, let line voltage be 235 kV. Okay, that is AC side line voltage is 235 kV, and let transmission line or DC line current be 1 kiloampere. So this is the given data. So I have to find the minimum cost of filter. So what is power transmitted? Let me find out. Power transmitted, PD is equal to VD into ID. What is the total voltage? It is a plus minus 300 kV. So this is plus 300 kV, this is minus 300 kV. Total voltage is plus 300 minus 300, that is 600. 600 into, and what is the DC line current? It is 1 kiloampere. So this is the total power. Total power therefore is 600 megawatts. So therefore a power of 600 megawatts is transmitted over the line. Let power factor of the converter input side power factor be 0.866. It's also given in the data. So therefore, if DC side power is 600 megawatts, what is AC side power? AC side power is given by 3 times fundamental component of voltage, phase voltage, into fundamental component of current into cos phi. Okay, so that is equal to 3. Say how many bridges are there? 1, 2, 3, 4. So I will multiply it by 4, because you see this is the voltage of one bridge. So since there are 4 bridges in series, so I have to multiply it by 4. 4 into 3 into, what is line voltage? I have already written here line voltage. It's actually line voltage. Line voltage is 235 kV. So it is 235. And what is there for phase voltage? I will write here phase voltage is 235 by root 3. Line voltage is 235 kV. So since I am taking per phase, 3V phase, I phase into cos phi. So phase voltage is 230 by root 3 into IL1 into power factor is 0.866. It's given here. So from this, what is, if we assume that converter has 0 losses, it does not have losses, so AC side power will be equal to DC side power. Since DC side power is 600 megawatts, AC side power will be also 600 megawatts. So 600 megawatts is equal to this. From this we can find line current. So line fundamental component of line current will be 1700 by 4 amperes. This is RMS value of line current. So for, let us suppose, let filter be designed for suppressing fifth harmonic component. We are now putting a filter here, and filter is designed to filter out the fifth harmonic component. So therefore, what is the fifth harmonic component of current? IH5 is equal to I5, that is equal to IL1 by 5. So that is equal to 85 amperes, because fundamental component of current we already know. What is the fundamental component of current? Line current, that is 1700 by 4. So if you have to find fifth harmonic component of current, that is fundamental component of current, that is IL1 by 5, that is 85 amperes. So what is UL? I want to find what is UL, cost of filter, inductor, and cost of capacitor per dollar. So now my V1 is equal to 235 by root 3 kV. Let it is given in the problem, UC, the cost of capacitor is, filter capacitor is $3.5 per kilowatt. $3.5 per kilowatt, and cost of filter inductor is $8.0 per kilowatt. It is given in the problem. I will write here, it is given in the problem. Now I have to find the total cost. So A is equal to UC plus UL by H square. UC is 3.5 plus UL is 8 by H is 5 square. So A is equal to $3.82 per kilowatt, and in terms of megawatt it is $3,820 per megawatt. Okay, this is A. What is B? B is given by, if you remember, V1 square IHF square by H into UC plus UL. You know, so this A and B we have already derived it previously, just few moments back. I am just substituting the values. So B is equal to, what is V1? V1 is 235 by root 3 square into IHF. अभी हमने निकाला, IHF is 85 amperes. So it is 85 into 10 raised power minus 3 kilo amperes. Divided by H is 5 into, what is the cost of capacitor? Cost of capacitor is 3500 per megawatt. 3500 plus, and cost of inductor is $8,000 per megawatt plus cost of UL is 8000. So substitute it here, so this will give you B. I have not calculated B. I advise you to calculate the B. Once you know the B, then you know what is S. What is the condition for minimum cost? Condition for minimum cost of filter is S equal to B by A. So therefore, what is minimum cost of filter? Minimum cost of filter is given by the expression. What is the expression for minimum cost of filter? Just few moments back. That is 2 under root of AB. You know A, you know B, substitute, this will give you minimum cost of filter. And total minimum cost of filter will be $71,000 per phase. So this is the minimum cost of filter. If you make simple substitutions in the equations, the minimum cost of filter is given by 2 under root AB. A and B you have found from above. You substitute here. So the minimum cost of filter will be $71,000 per phase. And the minimum cost will be somewhere here. It will be here. So your filter will be operating here. This much of reactive power compensation it will be doing, and its cost will be minimum cost somewhere here. This is how we find the minimum cost of filter. So to end my today's lecture, I will now discuss one more concept. That is, we will discuss effect of network impedance on filtering. Effect of network impedance on filtering. I mean, when you design a filter has certain impedance. It is connected across your AC network, but your AC network also has some impedance. So for example, if this is your converter, I will write here, this is my converter, and this is the filter. I am connecting filter across the converter. This is filter, and this is my AC network. AC network. They are connected in parallel. Let us suppose the current drawn by converter is IHC. Harmonic component of current drawn by the converter is IHC. Okay. Let us suppose filter, the current flowing through the filter is IHF, and filter impedance is ZHF. And let us suppose current going into the AC network is IHN, and AC network impedance is ZHN, and the AC network voltage is VH. Okay, and this is the voltage. Now our aim is that no harmonic component of current should enter the AC network. Whatever harmonics are generated by in the current by the converter, those all harmonics should be arrested by your filter. No harmonic component should flow here. Now I can write here VH, this voltage, VH, voltage across AC network corresponding to a particular harmonic frequency. It is given by harmonic component of current into ZHN. What is the harmonic component of current flowing through this AC network? IHN. And what is the impedance of AC network? ZHN. So I can write VH is equal to, now what is this IHN? I can, this IHN is the current which is going into the AC network, and this harmonic current is actually generated by the converter. So I can see this is, you can treat this converter as a current source, and then some current goes into the filter network and some goes into the AC network. The current which goes into AC network by current divider formula, that is given by impedance of the filter, opposite impedance. Current going into this network is the opposite opposite impedance ZFH divided by total impedance ZHF plus ZHN, ZHF plus ZHN, multiplied by what is the current coming from the current source, total current, that is IHC. Okay, this is the current which is going into the AC network multiplied by ZHN, multiplied by ZHN. So I can write by current divider formula, by current divider formula. So by current divider formula, I have found what is the current going into the AC network, IHN. IHN is ZHN, ZHF divided by ZHF plus ZHN into IHC. Then voltage across the AC network because of this harmonic component of current is IHN into ZHN. So this is IHN, यहाँ से यहाँ तक IHN है, multiplied by ZHN. Okay, that is it. So I can write it again like this. It is equal to IHC. I can rearrange it into ZHF divided by ZHN plus ZHF into ZHN. So this is the voltage across the AC network. Okay, so when ZHN is equal to 0, ZHN is equal to 0, I mean when the impedance of AC network is equal to 0, which is an unrealistic case. You can never have impedance of AC network 0. Then in that case, whole harmonic content, whole harmonic current goes to AC network. See, your harmonic current comes from the converter. Some of it is trapped by the filter and rest travels into the AC network. If AC network impedance is 0, and I mean an ideal case, not ideal case, an unrealistic case, then whatever harmonic current is generated here, it goes into the short circuit because AC network impedance is 0. All the current will flow into the AC network, which is undesirable, isn't it? So on the other hand, when ZHN is infinite, that means AC network impedance is infinite. So what is its impedance? Infinite. That means whatever harmonics are generated by the converter, all the harmonics flow into the filter. They are trapped by the filter. So in that case, whole harmonic current is trapped by filter, and no harmonic goes into the AC network. No harmonic flows into AC network. This is a desirable thing. We want this thing to happen. So for this thing to happen, the AC network impedance as compared to filter impedance should be infinite. But this is an ideal case. I will write here, this is ideal case. It's not possible to have AC network impedance infinite. Okay, it's not in our control. So therefore, desirable, what is desirable is that AC network impedance should be much higher than filter impedance. Okay, now as far as AC network impedance is, it is not in our control. not in our control. Whatever AC network is already there, your converter is connected to AC network, AC source through converter transformer. Whatever is the impedance of AC network, that depends upon the AC network configuration, and it is not at all in our control. We cannot make it infinite. We cannot increase it. We cannot decrease it. What is in our control is filter impedance. So filter impedance is controllable. So therefore, since filter impedance is controllable, we can create a condition where we can make filter impedance very, very small as compared to AC network impedance. Because AC network impedance we cannot change, it's fixed. But filter impedance, when we design the filter impedance we can change. So therefore, when we design the filter, okay, for trapping particular harmonic component of the current, okay, we have to design it in such a way that its impedance ZHF as compared to AC network impedance is negligibly small, so that almost all harmonic current which is generated by the converter, it flows into the filter, it is trapped by the filter, and negligible harmonic component of current enters the AC network. So this is how the AC network and filter, they interact with each other. So with this I will complete my today's lecture. So in our today's lecture, we try to discuss the design aspects of design of a single tune filter, and we have seen what are the conditions for designing a single tune filter and then double tune filter, and we have also seen how much reactive power is compensated or generated by a single tune filter or a double tune filter. We have got the mathematical expression for that, and we have seen that reactive power is always generated by the harmonic filter. It's not absorbed. It always generates the reactive power. And then we try to find the minimum cost of filter. We have found what is the condition for designing the filter for minimum cost. Because if you don't design the filter for minimum cost, then filter cost will be significantly high. Filter cost will be 10 to 15% of the terminal equipment cost of the HVDC system, which is very high cost. So to reduce the cost of filter, we have discussed the condition for minimum cost of filter. So we have found that the condition for minimum cost is that S should be equal to under root of B by A, S should be equal to A by B or B by A, something like that. That means the reactive power compensation that the filter has to provide, it should be governed by that equation. And then we have substituted that condition into the original equation, and we have found what is the minimum cost of filter. And we have found that minimum cost of filter, K min, is under root of 2 under root of AB. And we have taken an example, and with the help of that example, we tried to find what is the minimum cost of filter. So therefore, whenever you design the tuned filter for arresting or suppressing the harmonics, your filter provides some reactive power compensation also. You always should try to design it for minimum cost. And we have derived the condition for minimum cost, and we have seen how to find the minimum cost of the filter. And finally, we try to see what is the effect of network impedance on the filtering. If AC network impedance is very, very small as compared to filter impedance, okay, if AC network impedance is very small, when you design the filter, it will have some impedance ZHF, and if you design the filter in such a way that ZHF is very high as compared to ZHN, that means AC network impedance is negligibly small as compared to filter impedance. Then in that case, majority of the harmonics will flow into the AC network, which is not desirable. We want to trap these harmonics so that they do not flow into the AC network. So therefore, whenever you design the filter, you have to design it in such a way that the filter impedance is very, very small as compared to AC network impedance. Because AC network impedance is not in our control, but filter impedance is in our control. While designing the harmonic filter, we have to take care that this ZHF, that is the harmonic filter impedance, is very, very small as compared to ZHN, that is AC network impedance, so that more than 90% of the harmonics, they are trapped by the filter, and hardly any harmonics enter into the AC network. So this completes the first part of our module 5, that is harmonic analysis and harmonic filters, design of harmonic filters, how to find minimum cost of harmonic filters, and what is the effect of network impedance on filtering. So inshallah, in our next lecture, maybe tomorrow, we will try to discuss HVDC Lite or HVDC Plus, and if time permits, I will also discuss with you multi-terminal HVDC systems. We will try to finish our module tomorrow, or in one lecture, or at the most 2 lectures. So I advise you all to please go through this lecture, today's lecture and previous day's lecture. And in case of any difficulty, you can ask me the queries. Thank you.